Okay, today I'll be explaining chapter 9 homework. This is gonna be question 1. So for question 1, part A, we have the following. It says that we have a machine part rotating at 0.500 radians per second, and we have a constant angular acceleration of 2.50. They're asking us for the angle that the machine rotated when the speed was equal to 3.5. Okay, so let's go ahead and write down what we know. We know the initial rotating part. So let's write that down, which is gonna be 0.5 frames per second. And then we have the speed of the angle right here. It's gonna be right a square. And then we have the other one over here, which was 3.25 radians per second. Okay, so let's go ahead and use our formula. We're gonna use the angular acceleration formula. Let's go ahead. Okay, we are gonna use this one. It's gonna be square times the initial plus 2. It's gonna be for the angle. Okay, let's go ahead and plug it in what we know. We have that this is 3.25 square equals 0.5 square plus 2 times 250 times the angle, which is what we have to find out. So let's go ahead and solve for that angle so we can find it. So we have this, we move this to the other side, square it. Right here. This is gonna be 15. Let me put that over 5. Okay. So then we go ahead and put that into our angle, and it's gonna give us, when we put that in the calculator, it's gonna give us this number, 2.06 to 25 radians. So I'm just gonna use this part, 2.06. So that was the angle in radians. Let's go ahead and go with part B. Calculate the angle from part A in degrees. So we've previously done this before for all of the other chapters. So to calculate from radians to degrees, we are gonna put this right here. These are the radians. This is what we got. Times a radian, it's gonna be 180 degrees. It's gonna be over 3.1450, which equals 180 degrees. So then we get this. It's gonna be 180.17. This is gonna be the angle in degrees. Okay, let's see. Part C. Calculate the angle from part A in revolutions. So we're gonna go ahead and do the same, but in this case, we're just gonna do it by revolutions. So a revolution, it's gonna be, one revolution is gonna be 6.2831 radians. So we put that here so we can cancel out 2 point, and then we have the radians here. This is in radians. Radians cancel out times 1. This is in revolutions. I am sorry. And then we get that the revolution of part A is 0.32A in revolutions. So we got it from the angle in radians, 2 degrees, 2 revolutions. Okay, now for part D, we have a different question. Let me go ahead and write that down. Part D. It says the following. The rotor of a helicopter is gaining angular speed with constant angular acceleration. At time 0, it is rotating at 1.25 from t0 to 2 seconds and rotates through 8 point radians. What is the angular acceleration of the rotor? Okay, so let me go ahead and see what we have. We have this, we have this is what give us to us, which is gonna be to what it rotates through. So we have 8 point radians. Then we have the first one, which is gonna be 125 radians per second. And we have the time. The time is 2 seconds. Because in the question says, what is the angular acceleration of the rotor? So let's go ahead. We're gonna use the formula for this that we learned in this chapter. It's gonna be the angle equals acceleration times time plus put 2 AT. So in this case, we're using one of the old formulas, kinematic equation, but we are entering something from this chapter, which is gonna be this. Okay. Now let me go ahead and plug that in. Radians. So per second over, and this is going to be times 2 seconds, which is what they're asking us. That's going to be our time over 1.5. This and the other time. Let me simplify that. So we have 8 point radians minus 2.5 radians, which is what this was, equals 1.5. Then the off 2 point over, and then we get that the angular acceleration it's gonna be 2.75 radians second square, 10 per second square. So let's go ahead and go to part E. Through what angle in radians does the rotor rotates from 0 to 4? So in this case, we're just gonna use the same formula, but like we can see that we have different time. So we're just gonna plug in, instead of 2, we're gonna use 4. So T is gonna be 4 seconds. So same formula as before. Let's go ahead and plug that in. Radians per second, then 4 seconds in this case, plus 1.5, 2.75 radians square, and then 4, which is the time square. When we go ahead and do that, we get that the angle in radians, it's gonna be 27.0. 27.0 in radians. Okay, that is going to be part E of this question. Let's go ahead with the following question. Part F, a Ural's grinding wheel slows down at a constant rate from 185 radians to 105 radians per second while it rotates through 16 point revolutions. How much does this take? Okay, so let's see what we have. We have that slowing down from a rate to another, and it has a constant revolution. So let me go ahead and plug that down. This is gonna be part F. Okay, let's go ahead and use. Now we have to figure out what is it gonna be the revolutions of 16 revolutions. How much does this take? So let's convert that to radians to see how many revolutions that's gonna take. How many radians 16 revolutions is gonna take? Sorry. So we go ahead and do this. Equals 1 revolution. And then when we put that in our calculator, we see that 16 revolutions is gonna be about 153 radians. Okay, so we know that now. Now we're gonna head and use this following formula that we used before, which is gonna be the angular is gonna be the initial times time plus the angular times square. Okay, so let me go ahead and put that and plug it in what we have so far. So let's just do algebra for this formula because we need to see. They're asking us about how much time does it take. So we're gonna solve this and try to put time on the other side so we can have the formula to find time. So let's go ahead and do this on this side. This is just gonna be algebra that I'm doing right now. Initial times time, so we can bring it to the other side. Then we already multiplied this times time again. Okay, and now we're gonna move it to this side. So 4 angles times the radian, and t plus this, because we're getting rid of that 1.5. And then this is when we move the 2 from the other side. These two cancel out, and then we are almost getting there. Now we have this again. We're gonna make it into this plus the final one and a t to the side. We just put it to the other side, and then we get that our formula is gonna be the following plus the final one. Okay, now that we have this, we can actually plug in what we have. So time, what's time gonna be? 2 times how much is it gonna take for us to convert those 16 revolutions? We got that here, so let's go ahead and use that number, 53 radians, over the times that they gave us, which is gonna be 0.85 radians square times 105 radians square. When we go ahead and do this, we find that our time is going to be 0.693 seconds. That's going to be it for part F. Now let's go ahead and go to part G. Part G is one of those questions that we always have at the end. That's going to be just all algebra. So let's go ahead and do that. Part G. So let's see what it says. A disk rotates around an axis through its center. The disk has a line drawn on it that extends from the axis. At time equals 0, this line along the x-axis is rotating with positive angular velocity. They're giving us that. The disk has constant positive angular acceleration. At what time after time equals 0, the line on the disk rotated through angle. Okay, so let's see what we can use for this. So for part G, let's go ahead and use the same formula. So this is what we have. We have that as well, times 1.5. Then the acceleration times square. And let's go ahead and plug in what we have. So this is gonna be the same, and then this is gonna be the same, and then that. But what we notice from this is that we can combine them like terms. So when we do this, we get 1.5 with this, t squared plus final t, the angular velocity, t, and minus the angle equals 0. what do we notice from here? We have a quadratic equation. So let's go ahead and put that in our quadratic equation. Plus, it's always going to be plus because we don't need a negative number. Then here, just plug it in. We're just plugging this in. Our angle. And then the angular acceleration is going to be at the bottom. Okay. So for this, there's not much that we can do. We just have to plug it in and we cannot go forward after this. So what we have is that this is going to be our question and it's going to be positive because t must be positive. The time must be positive. And that's all.